Yeah. Tired getting how to do this. Okay. All right. 7.4. Equations and rational expressions. Equations with rational expressions and graphs. One option. All right. Let's see here. All right. So in this one, example one, we're basically, I guess in general, when we have rational expressions, let's just say we had x plus y plus z over a plus b plus c. Basically, it doesn't really matter what's in the bottom. Whatever it is cannot be zero. So for a rational expression, your domain is always going to be denominator not equal to zero. Because basically, if you divide by zero, you essentially explode and get an infinity. If you divide by zero, if you divide by zero, you basically end up going to infinity. Yeah. If you divide by infinity, you end up going to zero. Because think of a dollar divided up by a million people. If you divide them, how much money does everybody get? Practically nothing. That's why it works like that. Little more difficult to understand why dividing by zero get to infinity, but really that gets more into limits. Which if you keep going, maybe you'll get it in your calculus one if you actually go that far, or if not, you'll never get it ever. But either way, it's out there. So basically, let's look at example one. Okay, let's see here. So we have part A. We have 2x or 2 over x over 3 halves equals 7 over 2x. All right. So now the first thing we want to do, we want to so we want to find the domain of this thing. I see. Example 4 is where I stopped. So I actually got pretty far on this last class. Kind of really backtracking, but it's worth it, I guess. Don't feel like it's worth it right now, but it's worth it. All right, so basically, if I look at my denominators are x, 2, and 2x. So that is not equal to 0. This not equal to 0, which is automatic. So that poses no problem. And this is not equal to 0, which means that if I divide by 2, it means that x is not equal to 0, which we've already taken care of here. It's just an overlap. So basically, your domain is all x's such that x is not equal to 0. That's your domain. Now from here, I'm going to skip to, let's see here. It's a corresponding problem. Yeah, example 2. Example 2a. The same problem they're asking you to solve. So basically we're solving this problem. 2x minus 3/2 equals yada yada yada. So we basically have 2x, or 2 over x, sorry, minus 3/2 plus 7 over 2x, no, equals. So that's equal 7 over 2x. So let me do some erasing, clean this up a little. Okay. What is that glosh that doesn't want to go anywhere for some reason? I don't get that. Do not get that. It has to be stubborn. Yes, I just said gots to be. I'm tired. Gots to be. Alright. Screen. Pen. There we go. Just disappeared. I don't know what that is. Alright, so basically, the same as before, we want to just go, we don't like fractions, so let's just get rid of them in solving our equations. So basically, we can multiply by 2 and x to get rid of the 2 and the x in the denominator. So 2x, 2x. So basically, what I end up with is this divided by that, cancels, and I end up with 2. So if I distribute, I end up with 4 minus 3x equals 7. Yeah, 4 minus 3x equals 7, and as we would normally solve this, we end up with, I'm going to cut to the chase because we've done this a few times. So we have x equals, so I'm going to be 7. I'm going to subtract 7 minus 4 over minus 3, which is gracious, minus, so it's going to be 3 over minus 3, which is minus 1. No. Yeah, that's right. Okay, yeah. So 7. I'm sorry, I'm really tired. Okay, so x equals minus 1. Okay, so we're not quite done. We found a value of x that solved this. So we're saying that this value satisfies this equation. But there's values that this equation can't take on. Specifically, it can't be 0. So fortunately, this is not 0. So this is in the domain. So the domain is basically all real numbers except 0. So this falls within the domain. This is fine. So your solution will be x equals -1. So let's go back. And actually, example 2, I'm just going to stick with example 2 and just solve it all at once. So basically, we'll stick with example 2. And I'm going to call this example 2 a B, example 2b. And yeah, okay, so basically we have 2 over x minus 3 minus 3 over x plus 3 equals 12 over x squared minus 9. Alright, 12 over x squared minus 9. Okay. Getting delirious. Alright, so we have Okay, so we basically have, so we can go ahead and rewrite this as a product, and if we do, we're going to end up with x plus 3 and x minus 3. So basically, you can write this as 2 over, sorry, don't need that equal sign, x minus 3 minus 3 over x plus 3 equals 12 over x plus 3 times x minus 3. So now the common denominator here is going to be x plus 3 times x minus 3. So let's just go ahead and do that. 2 times x plus 3 over x minus 3 times x plus 3. Actually, I don't want to do that. Let's not do it that way. Let's not do it this way. It's correct, but there's a much easier way to go about this. Much easier way to go about this. What did I say before about fractions? We don't want to deal with fractions. So let's go ahead and do something to eliminate these fractions. Alright, so let's not do it that way. What I'm going to do instead is multiply by x plus 2, x plus 3 and x minus 3. So if I do that, I'll basically have 2 times x plus 3 if I multiply both of these on both sides. That's what I'm doing. So I have here minus 3 times x minus 3 equals, and multiplying by x plus 3 and x minus 3, they're just going to cancel. So I'm just going to have 12. All right. So basically I have 2x plus 6 minus 3x plus 9 equals 12. Plus 6 minus 12. Okay, and let's see here. If I simplify that, I get 2 minus x plus 15 equals minus 12, which means that x equals, so let's see here, if I subtract 15 from both sides, I get minus, well, we'll say minus x equals minus, let's see, 12 minus 12 minus 15, 12 plus 15 is 27. That's not right. Why do I have a I'm sorry, that should be positive 12. That should be a positive 12. I'm just crazy. Crazy, crazy, crazy. Okay. Gracious. More options. Screen. Pen. Okay. So actually, what we have is, yeah. So if I subtract 15 from both sides, I'm basically going to end up with 12 minus 15 is minus 3, so minus x equals minus 3, which means that x equals 3. So are we done? Almost. We found an answer, but is our answer valid? We need to check basically our domain, because notice here, and I'll go ahead and tell you ahead of time, if I plug 3 into here, I know I'm going to have a problem. So automatically you can kind of see you're not going to have a solution here. But let's go ahead like we did before. So basically you got x minus 3 not equal to 0, x plus 3 not equal to 0, and x plus 9 x squared minus 9. Oops. Okay, so none of this can be 0. This means that x cannot be 3. This means that x cannot be minus 3. And since this is x plus 3 times x minus 3, that means that x cannot be 3 and x cannot be minus 3. X can't be 3. So basically this is sort of repetitive. This we already found it based on these. So this is kind of repetitive. But basically our domain is all x's such that x is not equal to plus 3 or minus 3. So that's our domain. So basically this is equal. This is saying to solve this problem, to solve this, x has to be 3. But x cannot be 3, so there is no solution. So basically your solution is empty set this, basically any of those is acceptable. They all mean the same thing. And I guess I'm left-handed, so I kind of write the little thing backwards, but I guess the book writes the empty set like this, which is really hard for me to do being left-handed. But I will accept either. I will accept either. I would hope anyone would accept either, but I don't know. Some people might be sticklers about that kind of thing. And let me make sure I'm recording, because I would hate to have recorded all of this and did all of this and not be recording. So okay, yep, the timers are going. All right, back to it. Current slide. No, I don't want to present online. I guess I should save. Alright, from current slide. There we go. Alright. What example did I just do? 2. Alright, so I'm on example 3. Alright. And actually this was a combination of example 1 and yeah, I just combined example 1 and example 2 basically, because they're very closely related. One's about the domain alone and one's about the solution. But I want you to keep in mind that the domain is very important in solving a rational equation, because you have to take it into account. You cannot divide by 0. So if you solve something and the solution requires you to divide by 0, then it's not a solution. Unless you're trying to solve for when the equation gives you infinity, in which case it's still, to a degree, be nonsense. Alright, and okay, I'm sorry. That was not example 2. That was actually, I can't erase now. This was not example 2. This was example 3. Let's see here. Pointer options. So this actually was 3. Alright, I guess I thought they lumped it together, but this wasn't. I thought it was 2B, but it's actually 3. It doesn't really make any difference for the math, but if you're trying to keep track in your book, this is actually example 3. There's just 3 examples left. No? Okay. Alright, so Example 4. Yeah. And I think this is where we stopped in class. All right, so this is a long one. 3 over p squared plus p minus 2 minus 1 over p squared minus 1 equals 7 over 2 times p squared plus 3p plus 2. Double check that I wrote this correctly. 3 okay. Alright, so the first thing we want to do is go ahead and see if we can factor the denominators. In this case, I believe we can. We'll just end up with, if we factor this, actually let me just go ahead and do it together. Okay. All right. So we have 3 over something p something minus. This is going to be p plus 1 p minus 1, obviously. Difference of 2 squares, and that's going to be 7 over 2. Or maybe I shouldn't say obviously. Maybe that's may not be as easy to see as I perceive. Okay, so now let's look at the first one. So we basically have factors of -2 that add to 1. So plus 2 and -1. Here we want factors of 2 that add to 3, which is just going to be plus 1 plus 2. And the middle one, we're all good there. Alright, so now let's multiply by. Alright, so what do we have in the bottom? We have p minus 1. We have p plus 2. And that's it. So we can multiply by p minus 1 times p plus 2 to get rid of all of our. There's one thing I'm leaving off. There's p plus 1. Yeah, so we got p minus 1, p plus 1, and p plus 2. So if we multiply by all 3 of these, we should get rid of all of our fractions. Okay, so I'll go ahead and do that. So if I do that here, I'll get 3 times, so p minus 1 is going to cancel, p plus 2 is going to cancel, so all it's going to be left is p. That's going to be a problem. Okay, so let me erase this. Make room for myself. Just keep that in mind. These are the 3 denominators, 3 things we need to multiply by. Okay, so let's see if clear. What are the order? Alright. Pointer options pen. Alright, so we're going to be left with 3 times the only thing we don't have here is p plus 1 minus 1 times the only thing we don't have here is p plus 2 equals 7 times p minus 1. So we're going to have 3p plus 3 minus p minus 2 equals 7p minus 7. Did I leave something off here? Oh, right. That is over. Oh, there's also a 2 down here. So we need to multiply everything by 2 to get rid of that 2. So let's do this times 2. So this is going to be times 2. This is going to be times 2. And this 7 over 2 times 2 is just going to be 7. So does everybody catch that? I dropped the 2 right there. So we had a 2 in the denominator also. So basically we had this, this, and the 2. All multiply all 4 of those to everything to get rid of all my fractions. Because otherwise I would have had 7 over 2 instead. So I can get rid of that also. So, hope you follow that. Again, if you don't follow that, please ask questions either in class or email me, one of the two, or maybe there's other methods I can't think of right now, but just communicate. The whole point is communicate with me, I guess is the point that I'm trying to make. Alright, so we have basically 6p plus 6. So 6p plus 6, because that's his 6. Yeah, that gives you 6. And this was actually 2 times 1, which gave you 2. Because remember, there's a 1 here, because this 1 was multiplied by 2, this 3 was multiplied by 2, and this 7 over 2 was multiplied by 2 just to leave 7. Right. So, and that should be right. And let me double check this. Yeah, and that's wrong. So that should be 2p. So that's 2p. And 2 times 2 is 4. Okay. So we have 6p plus 6 minus p minus 4, 2p minus 4. Hey. Sorry guys, I think I need to, well, I guess I can't call it quits because I need to finish this today. Let's see here. So, okay, so that's what we need. Alright, so basically if I combine like terms, I end up with 4p and plus 2 equals 7p minus 7, and we end up with, so to avoid dealing with negatives, I'll just do 4 subtract that from those, and I end up with 2 equals 3p minus 7. And I'm adding in all the steps because I am really tired right now and I don't want to make any mistakes. Equals 3p, which means that p equals 3, or vice versa. So anyway, p equals 3. So, is that valid? Let's check our domain. Basically, we got these 3, this times this, this times this, and this times this can't be 0, which means that basically p minus 1 can't be 0, p plus 2 not equals 0, p plus 1 not equals 0, and else. And of course, I guess if you want to be technical about it, 2 is not equal to 0 because 2 is in a denominator. This is, yeah, that's pretty much automatically satisfied. And then, so this means that P is not equal to 1, P not equal to minus 2, and P is not equal to minus 1. So basically, your domain is excludes these three numbers. So basically, all reals except 1, minus 1, and minus 2. 1 minus 1 minus 2. Yeah. Okay. So basically, if you look at our solution, we got P equals 3. So yes, you can use that. It is a solution. It's usable. All right. And example 5. I gotta take a break. Alrighty, back where we left off. Oh no. Current slide. I wonder if this is easier to see. Oops. Yeah. Okay. Alright, back at it. Example 5. Alright, again, we're asked to solve 2 over 3x plus 1 equals 1 over x minus 6x over 3x plus 1. 3 over 2 over 3x plus 1 equals 1 over x minus 6 over 1. Alright. So, looking at this, we should be used to this a little bit by now. This basically means that x is not equal to 0 and x is not equal to minus 1/3. And I'll let you figure out the first one's pretty self-explanatory. I'll let you try to play with it and figure out why the second one is. Why x is not negative 1/3. Alright, so basically we're going to multiply everything by, to get rid of our fractions, we can just multiply by 3x plus 1, multiply by x, and we'll be rid of our fractions. So it's going to basically end up being 2x equals 1 times 3x plus 1 minus 6x times x, basically. Yeah, because if I remember, I'm multiplying by both x and 3x plus 1, so 3x plus 1 is going to cancel and leave x in the top. Same thing, except here may not be as clear. I already don't get confused. I already had an x here from the 6x, but I had 3x plus 1 in the denominator. The x is still going to be multiplied in the numerator, so it's going to end up being x squared. So I end up with 2x equals 3x plus 1 minus 6x squared. So now So now we basically have a quadratic, and when we have a quadratic, what do we always do? We need to get everything on one side. So we have 6x squared is our quadratic term, and then our linear terms are 3x or 2x minus 3x, which is minus x, and then minus 1 equals 0. So now I can write this as just a moment. Pause this thing again. Yeah, I keep having a stop and go on this one, but at any rate, current slide. Okay, so basically, screen. Alright, so basically from what we did before, I'm not going to go through the whole factoring process, but we'll end up, if we factor this, we'll end up with 3x plus 1 and 2x minus 1 equal to 0. So that basically that means that either this has to be 0 or this has to be 0. So in other words, 3x plus 1 equals 0, or 2x minus 1 equals 0, which means that x equals minus 1/3, or x equals 1/2. Alright, so if we look at these two results, negative 1/3, is that okay? Let's look at our domain. Up. You can't use that. What about 1/2? 1/2 is fine. It's in our domain. So basically, we end up throwing away one of our solutions to end up with just a solution of x equals 1/2. And if you wanted to check our answer, we can plug 1/2 back in to, I guess here would probably be the easiest place to plug it back in. But I'll leave it to you to try that. You should be doing that in your exams, checking your answers. Let me pause one more time. Now, before we get into example 6, I guess I should discuss one thing. Let's see. So let me just cross that out for the time being. All right. So basically, the graph of a rational function. A rational function is basically what we've been doing. You basically just have a ratio. You can have a number over a linear, or you can have a number over a quadratic, or quadratic over a cubic, or something along those lines. But basically, the result is the main thing that makes a rational function have its shape is the fact that you have these holes in the graph. You notice that you have a domain that skips an individual value. Like here, it skipped 1/3 here, and it skipped 0. So for one specific type of rational function is Now, this is not the only type of rational function. There's plenty of other types, because this is one specific one we'll talk about the graph for. Basically, the graph for this, if we have a grid, I'm going to try to draw free-handed. It's basically going to look like this. Now, it's not perfect. You can look at your book on page, what is this? For a better figure, this is on page 389 of your text, but basically the graph of 1 over x is going to look like this. I'm going to leave it as an exercise to you to get some, you should pick some x and y values and plot them for this function and see what you get. I'm not going to do it for you because, you know, you can sit here watching me do it all day. It's not going to help you one bit. But what I want you to do is just as an exercise, just kind of play with some numbers and see what you get when you plot this thing. But the key thing to get at here is that this line, in this case, 1 over x, what can't x be? X can't be 0. So basically, this line gets closer and closer and closer and closer to 0, but never touches it. Just like here, it gets close to 0, but it never actually touches it and never actually crosses it. So basically, this graph is forced on to stay on this side, and this section is forced to stay on this side. Okay, and that's basically how these things get their shape. And it also has a so this is called a vertical asymptote. And you notice the same thing happens. No. This is the x-axis, this is the y-axis. Okay, you notice the same thing happens on the y-axis, the x-axis basically. And it's horizontal, so this is the horizontal asymptote. And so this is your horizontal asymptote, is the x-axis, and your vertical asymptote is the y-axis, basically for this graph. If you know the difference between horizontal and vertical, you should be fine with this. Just know the word asymptote. So basically your domain clearly is x such that x not equal to 0. Now, let's say you didn't let's say you didn't know what this value of this was, okay? And let's just say you wanted to figure out my range. So basically your range is a set of y values. So let me go to another slide here. All right. So I'm going to look at 1 over x. So y equals 1 over x. What can't y be? It kind of takes a little bit of inspection, so to speak, and kind of understanding what actually happens here. Can y be positive? So let's just see. Let's just check. Let's check if y can be negative. Well, let me just pick some value. Negative 10. Okay, if I pick negative 10, I get 1 over negative 10. Okay, that's fine. There's nothing wrong with that. So we know we got a graph with a hole in it at 0. For my x's, but I won't even worry about that. Let's not even concern ourselves with this for the time being. But basically, if I plug in something that's negative, okay, I can't do that. I know what about a positive value? So let's see here. Oh, excuse me, goodness. A little bit tired. I'm not plugging in X, I'm plugging in Y, I'm plugging in X. So basically, let's just see, if I plugged in a negative value for X, I get a negative value for Y, right? Excuse me for that. If I plug in a negative value for X, I get a negative value for Y, right? Let's just say X equals negative 10. What if I plug in a positive X? Let's just say that X equals plus 10. Well, what's Y going to be? Y is going to be 1 over 10. That's fine. There's no problem with that. The sign that comes out doesn't even really matter. But is there a way, can Y be 0? So I can see that Y can be less than 0. I can see that Y can be greater than 0. But is it possible for Y to be 0? What do I have to do to make Y 0? Well, let's see. If Y equals 0, that means that 0 equals 1 over X, which means that basically 0 times X equals 1, which means that 0 equals 1, which is nonsense. So basically, that's why you have this horizontal asymptote here. Oh, excuse me. That's why you have this vertical asymptote here. You know, Y can't be 0. It's clear why X. Goodness. I'm sorry. Let me take a breath. Yeah, let me take a breath. All right. From this, it's clear why excuse me. Go back. Where's the page? What page? Yeah, it's clear why X can't be 0. So it's this part. This vertical asymptote is pretty clear. X can't be 0. Okay, and because I can't divide by 0. This horizontal asymptote, not so clear. But now that we look at it here, we can see that if we try to make Y equal 0, which really, I guess I could have cut out all this work. Really, this is more for demonstration purposes, and just cut straight to the chase and say, what if Y equals 0? Well, if Y equals 0, then that means that 0 equals 1, which is nonsense. So it's just not possible for Y to equal 0. But between this page and this page, it's not really that dire that you can reproduce this, but I'm just trying to demonstrate why this is. So basically, if we move on to our example, let's go on to example 6. And if you have questions on this, please ask me in class, because I realize this may not be as clear, and I may not have explained as well as I would have hoped to, but I can't rewind this darn thing. All right, so example 6. All right, but overall, just get the main basic idea of what this is. So let's just see. We have g of x equals minus 2 over x minus 3. So basically, what you have so you want to find the horizontal and vertical asymptotes. Excuse me. Excuse me. So you want to find the horizontal and Horizontal and vertical asymptotes is this thing. So basically, the horizontal asymptote is basically asking you, remember what's what. You got a coordinate system, you got an X, and you got a Y, right? So your horizontal asymptote, horizontal is flat. If you're talking about something that's flat, whatever it is, you're basically saying, okay, asymptote means what can't Y be? And your vertical asymptote is so basically if I look at this, I want to figure out what can't X be. Okay, so I got X into my denominator. Then that means that X minus 3 can't be 0, which means that X is not equal to 3. So my horizontal asymptote is, excuse me, no, my vertical asymptote, because if you look at that's why it's good to draw this figure, your vertical asymptote for X, because you're saying what can't X be, so you're going to say X equals 3. So basically the line X equals 3 is going to be my vertical asymptote. Okay. Because your asymptote, just like here, is a line. In this case, for 1 over X, your asymptote was just the lines Y equals 0 and X equals 0. Here, your asymptote, well, let me write that here. So so vertical asymptote is X equals 0. Your horizontal asymptote is Y equals 0. So those are your two asymptotes for 1 over X. For what we have now, your vertical asymptote is X equals 3. Alright, so in this case, Y equals G of X. So can Y be basically, if I got so have I really changed the condition? Let's see if Y equals 0 is possible. Let's see here. So if I got a fraction, if I got a number, basically if I start with a number and I divide it by anything, it's never going to give me 0. No matter how many times I divide something, I'm always going to get something. I can't divide something and get nothing. Okay, it's just not possible to divide something into nothing unless you somehow found a way to divide it by infinity. Okay, so that's just not going to happen. Unless you found a way to divide by infinity, it's just not going to happen. So basically, you know that Y is not equal to 0. So in this case, there's nothing really changes. Your X, your vertical asymptote shifts, but your horizontal asymptote is just going to be at Y equals 0. So basically, if we graph this, try to do a little bigger this time. We have an X, we have Y. And we'll say that our vertical asymptote is at, and for asymptotes, we just draw dashed lines basically. So we'll go 1, 2, 3. So we'll just do a dashed line here for our vertical asymptote at This is x equal 3. And we'll do a horizontal asymptote at y equals 0, which you can't really see, but I'll do it in another color. I guess I'll do it in black. This is your horizontal. Ugh, really bad with the words horizontal and vertical. Okay, this is your horizontal asymptote, and this is your vertical asymptote. So now, if I actually graph this thing, now notice basically all of I have a negative sign, so I could pull this out in front. So basically, what's going to end up happening if I pull that negative sign out in front is, notice that this was your original graph where I had it in this quadrant, in this quadrant. Well, if I make everything the negative of what it is, what's going to happen? This is going to move down here, and this is going to move up here. So that's basically what I'm going to have. What's going to happen? So basically, your asymptote shifts, and then your graph ends up moving. Remember, what you started off with was this. So what you're going to end up with is this. And this. And again, what you need to do, and what the book has you do, and I'm going to tell you to do this as an exercise, and I'm going to write all these points out and do dot to dot. Get you some x's, get you some y's, based on g of x, or in other words, some x's and some, to be more precise, some g of x's. So plot x, so do x and g of x, and see what happens. So you can do 3, for example, it's centered at 3, so you probably should do 3, 2, 1, maybe do 3, 2, 1, and maybe do 4, 5, just to get an idea of, just so you can see how this graph does, and do some points in between. So you should end up getting some dots that basically end up plotting this curve. But I'm just sort of showing you how to look at an equation and get this curve, but it's hard to tell just from plotting this. Excuse me, I gotta go blow my nose. I'll be right back. Pause this thing for another instance. Keep. What's wrong with it? What's wrong? Don't crash on my computer. Keep. Alright. Yeah, there was one, well, I won't call it a small error, but error in my drawing that I just made. If I go back, yeah, I said one thing and drew another, but basically the graph should be the negative. So this is going to be down here, and this is going to be up here. I kind of made that small mistake. I'll go over that more in class, but that's a little small error that I made. I guess just for my own fatigue. But I hope you guys got the idea of how to do that, basically. But